Hello, folks. We are going to finish up the Chapter 16 homework. Chapter 16, which is the last of the aquatic chapter. So we're going to look at problems 1, 2, 4, and 6. This is a little bit more heavy of math, so try to stick with me. So problem 1. A city's drinking water supply has a pH of 7.2. After filtration, and chlorine is to be added as an agent for disinfectant. So calculate the ratio of HOCl, hypochlorous acid, versus the hypochlorite in the solution after chlorine is added. What can be done to improve the conditions for disinfecting? So the hint is I utilize our Ka expression. The Ka is that HOCl reversibly goes to H plus and OCl minus. So, first step is to find the Ka of this value of this reaction, which we can look up, and I give you in the hint of Ka is 3 times 10 to the negative 8th. Once we have those values, finding the ratio of these is actually trivial because a pH of 7.2, so H plus concentration is equal to 10 to the negative 7.2, which is 6.3, let's say 31 times 10 to the negative 8th. So 3 times 10 to the negative 8th equals 6.31 times 10 to the negative 8th OCl minus over HOCl. Getting that to the other side, 3 divided by 6.31, we have a ratio of HOCl, if that's 1, and that's 1 minus x, 1.47, so we get 0.475, 1 and 6. Which I'm just trying to 1. Okay, so 1 minus 0.475, so 1 minus 0.475, we get x equals 0.525 joules. So whatever, okay. I'm just trying to figure out, but I mean, basically the ratio is OCl minus over HOCl is 0.475 to 1. So that's 0.475. If we invert that, it's basically a 2.1 to 1 ratio. 2.1 to 1 ratio of hypochlorite to chlorite. So how would you make more hypochlorous acid, which is the key for disinfectant? Would lower the pH, possibly by adding HCl. We just want to drop the pH less than 7 is sufficient to get the ratio of HOCl up. Just below 7 is already going to, so it would be 3 divided by, well, basically 10 divided by 3. You would have a ratio of, if it was just at 7 exactly, it's already 3.3 to 1. If you keep going, it's going to get higher and higher and higher, and so it's going to be more disinfectant. Okay. 2. Estimate the total organic carbon concentration of wastewater whose chemical oxygen demand is 500, COD is 500 milligrams per liter. What fraction of the total dissolved and particulate content of 720 milligrams per liter is then made organic material? So, if we said the TOS is 720, and we're wondering what or TS is 720 milligrams per liter, so how much of that? It must be from organic matter. Assume the organic fraction can be represented as CH2O. What might the remaining solids remain? So we need to convert the chemical oxygen demand into millimoles of oxygen per liter and calculate the oxidation rate. Millimole. So we need to figure out how much carbon can do. So basically our reaction is biomass plus oxygen converts to CO2 plus water. So with that in mind, 500 milligrams per liter, we have, if that is in 1 millimole, that is going to be 32 milligrams. Like usual, we did this one in the last chapter. So 500 divided by 32 is going to be, okay, it's going to be something like, it's going to react with 15.6 millimoles per liter. Okay. For every 1 millimole per liter, it's going to, for every 1 millimole of oxygen, it's going to react with 1 millimole of carbon. And 1 millimole of carbon is going to weigh this structure 12 plus 2 plus 16. 16 plus 2 plus 12 is 30. That's going to weigh about 30 it's going to be 30 milligrams per 1 millimole. So at 15.6 times 30, that means we would have something like 468 milligrams per liter of that carbon. So with that in mind, Now, let's see, what is, looking at exactly, that is how much of organic fraction. We want to see how much of this made of organic matter, so that's the answer. What fraction of this? So if we're just looking at this biomass, so 460, so 720 minus 468, 720 minus 468, going to give you something like, that's 252 milligrams of inorganics. So 468 out of 720, this is about 65%. 65% organic matter. With that in mind, 65% organic matter, approximately what, some of this can be in the form of what's the rest? Some of this can be in the form of phosphorus and nitrogens, but this number's still high, so it's still high in colloid. So it could be phosphates and nitrates, could be some clay, could be some hydrous iron oxide or aluminum oxide, maybe some carbonates with some simple calcium, magnesium. But that is more up to speculation than actual straight up numbers. So leaving off at 4. Number 4, another math problem. A wastewater contains 7.2 milligrams per liter of phosphorus and is treated with 15 milligrams per liter of aluminum in the form of an alum solution. Assume the phosphorus is precipitated in the following reaction. Aluminum 3 plus phosphate goes to AlPO4, and that any excess aluminum gets converted into aluminum trihydroxide. Indicate the mass of inorganic sludge produced in one day in a plant that treats 20,000 cubic meters of wastewater. So one of the things we need to figure out is how much volume is 20,000 cubic meters. 20,000 cubic meters is, there is 1,000 liters per cubic meter. So this is, we're treating 2 times 10 to the 7th liters of wastewater. I'm going to go ahead and convert these now. So 7.2 milligrams of phosphorus times 2 times 10 to the 7th. So, and I'm going to divide by 1,000, so that, and 1,000 again. So this is something like, we're producing 144 kilograms of phosphorus, and we're treating this with, treated with 300 kilograms of aluminum. Okay. Now with that in mind, we need to figure out the weights. The weights of these guys. The weight of aluminum is about 27. The weight of phosphorus is about 31. I'm rounding these guys roughly, but 144 divided by 31. 144 divided by 31 is something like 4.645 kilomoles, and 300 divided by 27, 300 divided by 27 is something like 1.11 kilomoles. So, wait. Oh, that's, no, sorry, 11.11 kilomoles. So, now, that's moles of aluminum. So every 1 mole of aluminum reacts with 1 mole of phosphorus. So with that in mind, we will produce, what is the limiting reactant? The limiting reactant is phosphorus. We will produce 4.65 kilomoles of aluminum phosphate, and whatever is remaining is going to go into aluminum oxide. So 11.11, 4.65. So that means we have 6.46 kilomoles of aluminum hydroxide. So, to figure out the mass, 17 times 3 plus 27, that's something like 78 grams. 27 plus 31 plus 16 times 4, that is something like 122 grams per mole. So with that in mind, 4.65 times 122. 122, this is going to give us 567.3 kilograms, and 6.46 times 78 going to give us something like 503.9 kilograms, And when we add those together, how much waste would we produce total? Total waste is something like 1,071 kilograms. Well, kilograms total waste. So I'm just adding them together, and that's the total waste when I add them together. There's many different orders you could do this in, but the idea here is we're figuring out what is the waste we produced, and that is how much we produced. Okay, last problem. Acetylene tank treating 5.5 times 10 to the 6th liters of water per day has a dimension as follows: 12.2 long, 7 wide, and depth of 3.5 meters. Calculate the detention time of the water in the tank. Calculate the minimum particle size expressed as diameter of spheres that could settle in the tank. So step 1 is to calculate the volume, which is just length times width times height. So 12.2 times 7 times 3.5. How much water? 298.9 meters cubed. Once again, we have to convert meters cubed into liters. So 1,000 liters in 1 meter cubed means, essentially, this 298,900 liters. It could hold that many liters. And however, if we're treating 5.5 times 10 to the 6th per day, we got to figure out how many times do we have to empty and fill this tank before that happen, with that volume. So I'm going to divide that by 5.5 times 10 to the 6th. So by 5.5, 10 power 6, that means per day that we have to so liters per tub. We have to work this through. So I guess it'd be the other way around. We might want to go the other way around. 5.5. I'll just invert that. The actual way we want to do that, if this is per tub, we want to say tubs per day. How many times do we have to fill the tubs per day? So in reality, it's more like 5.5 times 10 to the 6 liters per day, and you're dividing by 2.989 10 to the 5th liters per tub, and that means we fill the tub approximately 18.4 tubs per day. 18.4 tubs per day. Now, with that in mind, how long is that? Does each tub get per hour, per minute, per second? Because we really need this in seconds. So there's 24 hours in a day. So we're going to multiply that by 24. Multiply that by 24. So times 24. Then there's 60 minutes in an hour. 60 minutes in an hour. Actually, so it's the other way around. I need to divide. What am I doing? So in one day, there's 24 hours. And then for 1 hour, there's 60 minutes. And for 1 minute, there's 60 seconds. What am I doing wrong? I'm doing something. No, okay. Tubs per day. No, yeah, okay. I'm doing this. Okay. 18.4. This is still right. But, okay. How long per tub is this thing? So, yeah. 18.4. So, 24 hours in a day. And we're going to divide that by the day per 18.4 tubs. That's the trick. 24 divided by 18.4. So the particles, the tubs stays filled up about 1.3 hours. You need every 1.3 hours we have a new tub. So how many seconds is that? How many seconds is that? That is every 4,695.7 seconds we have a new tub. That's how long each tub stays filled. Now, for that settling velocity. We got to figure out what velocity allows it to settle this much. So we're trying to find the particle density, so we have to make some assumptions. Our velocity is equal to... so the velocity is, in this case, the distance it has to travel in meters divided by the time in seconds. So if it has to go 3.5 meters and 4,695.7, it's times by 1,000 to get this in millimeters. Let's time by another 1,000 to get into micrometers. So this is the settling velocity is something like 745.3 micrometers per second. That's our settling velocity. So we need to figure out what is okay. Millimeters. Yeah. I think okay. Now with that in mind, I think I've done it right. So with that in mind, the settling equation is V sub t equals the density of the particle minus the density of water all over 18 mu times gravity times the diameter of the particle squared. We're making some assumptions that the density of water is 1 times 10 to the third kilograms per meter cubed. We're going to assume the particle density is 2.65 times 10 to the third kilograms per meter cubed. And the particle, the slip velocity is 1 times 10 to the negative third kilograms per meter second. And gravity is 9.8 meters per second squared. Okay. So now the key is watching my units very carefully, as I do this. So, the reason I chose that particle density, because that's the example they have in the book. Otherwise, it's kind of hard to do this. Okay. So 745.4 micrometers per second. Let's see, 2650 minus 1,000 times 9.8 times diameter squared over 18 times 1 times 10 to the negative third. So that's 2650 minus 1,000 divided by 18 divided by 10 to the negative third times gravity, and we get something like 8.98 times 10 to the fifth diameter squared. So that's just looking at units. That's per meter cubed, kilograms per meter cubed. This is meters per second squared. This is kilograms per meter second. So what we have here is kilograms over meter cubed, meter second squared, with meters, seconds, and kilograms and diameter. So kilograms, seconds with 1 to the seconds. So 10 to the fifth. If I wanted to convert that into micrometers, so 1 meter, there is 10 to the sixth micrometers, would have 0.898 d squared equals 745.4 micrometers. That should work it out. So 745.4 divided by 0.898. So it gives me 830.06 micrometers squared equals d squared. So the particle diameter, when I square that, when I take the square root of that, should be in micrometers. So the particle size that can be separated by doing this should be something like 28.8 micrometers. 28.8 micrometers. The key here is to really, really, really watch your units. Most of these numbers I pulled from the book. Book, as an example for water, that's given. Water, given. I had to watch the units to make sure everything was worked out. But with that in mind, this tank could settle out any particle that is 28.8 micrometers or larger. Any smaller, and they won't settle in time, fully settle in time before the tub is replaced. So with that in mind, that is the end of this problem. This is the end of this problem set. Hopefully you could follow this. I know this one was a little trickier, but we're basically breaking it down again. We found out the tub dimension and how many tubs do we have to fill and empty to use up all that water. Now that we know how many times the tub gets filled and emptied, we can figure out how long does any one tub stay full in a 24-hour period. So we figured out how long does it take, does the water spend in any given tub. With that in mind, if we know how long the water can spend, we can figure out how long will it take for a particle to get from the surface to the bottom of that 3.5 meter tub. And finally, from that, we used our settling velocity equation to calculate how big of particles would settle in that tub with that settling velocity or higher. Okay, with that in mind, that is the end of that problem. Have a good day. Adios. See ya.